us now quickly look at the another concept here in the chapter Basic Mathematics, which is of logarithms. So what is logarithms? So next, let us start with the topic of logarithms. This was basically discovered and started by John Napier, who devised this technique in order to simplify calculations. This is also used in many applications where the calculations are involved of very high magnitude. Generally, the earthquake is measured, the degree of the earthquake that happens is measured in Richter scale, where logarithms is used. So let us understand how do we represent logarithms. So if A, B and C are three real numbers such that A to the power B is equal to C, then we can reversibly write this equation as log of C to the base A is equal to B. So basically here what happens is this number is written little below than the normal line, and this is known as the base, and B is the output of log C to the base A. In order to remember this, you can take it in the following manner. The base raised to the answer gives us the value of C, or you can also remember it in the following way. A raised to B is equal to C if, let us say, if somewhere it is written log of some number B to the base A, it simply means this is, if this is equal to X, then we can write X is a number such that A raised to X gives us B. Now there are a few conditions which we need to understand. Now here the number C, for which we are trying to find the logarithm, should always be greater than 0. The base A should be greater than 0 again, and it should not be equal to 1. So these are a few things which should be understood. Now I'm sure you might have already studied logarithms in your previous classes. So here we are just discussing this in brief. If A to the power B is equal to C, then we can write log of C base A is equal to B, and B is basically such a number. When raised to the power of A, it gives us the number C, and base to the, so this is how you should put in your mind. This arrow should give you a hint as to how you'll get an answer. If you want to remove logarithm, we take B to the power of A, and then that gives us C. So there are a few properties related to logarithms which we must remember. So let me revise for you the properties related to logarithms. The first property here is log of A into B base C is equal to log of A base C plus log of B base C. You can prove this very easily by your own self, so we will not get into the detail of the proof of these properties. Second one is log of A by B to the base C is equal to log A base C minus log B base C. These are the first few properties. Now here, when the two numbers were multiplied, if we want to separate it, it just becomes an addition, and in case the numbers are divided a upon b and there is a log, we can write it as a difference of these two numbers. The third property here is log of a raised to b power c. So here a is raised to power b. This is equal to b log a base c. So basically the exponent of a comes in front of log, and we simply write b times log of a into c. This can be, you can take the help of first property to understand the third property. Property number 4 is logarithm of any number to the same base. So here the base and the number for which we are trying to find the logarithm is the same, then the answer is always going to be 1. And the fifth property is logarithm of 1 to any base, let us say a, is always going to be 0. So these are first few properties which you need to remember. Now there is another sixth property which says a to the power log b base a is simply equal to b. You can prove this easily. How? Let us try to understand. Now suppose a raised to log b of a, b base a is equal to t. Now what we want to do is, we want to take log on both sides to the base a. So if we do that, we have log a raised to log of b base a to the base a. This is equal to log t base a. Now since this is the exponent of a, this will come in the front. So what we have is log b base a into log a base a, and this is equal to log t base a. Now since log a base a is 1, what we are left with is log b of b base a is equal to log t base a, which implies b is nothing but equal to t. So in this way you can simply prove property number 6. Let us now quickly look at the seventh property. The seventh property says log a base b can be written as log of a to some other base c upon log b to some other base to the same base c. So in this way, if you want to bring in some other base instead of a base which is given as, let us say, b, you can write it in the form of log of a to the base c, and you have to use the same base in the denominator where we take log of b. So these are some of the few properties related to logarithms. Let us quickly solve one question based on this. So let us say the question is log of x base 3 plus log of x square base 9 plus log of x cube base 27 is equal to 9. If this is the given condition, then find the value of x. So let us quickly see how we can solve this question. Now here the base are different. In the first log we have 3, in the second log we have 9, and in the third base we have 27. So let us try to make the base uniform. So we can write this as log x base 3 plus log x square upon, now let us take base 3 here, upon log 3 square base 3. Now here we are using the seventh property. We want the base to be 3, and hence we have written this in the fraction form. And now we can write this as log x cube base 3 upon log 27 can be written as 3 cube base 3. Now here if we simplify this, we have, from here we have log x base 3. From here 2 comes in the front. From here also 2 comes ahead of log, and log 3 base 3 becomes 1. So what we have is 2 upon 2 log x base 3. Then we have plus, here again same thing happens, and we can write it as 3 upon 3 log x base 3. So 2 and 2 cancels, 3 and 3 cancels. So what we all have is log x base 3 plus log x base 3 plus log x base 3. And therefore 3 log x base 3 is equal to 9 is what is given to us. Now clearly we can cancel out 3 and 9 because 9 is certainly a multiple of 3, and now we know how to write it. 3 raised to 3 will give us x. So we can write x is nothing but 3 raised to 3, which is equal to 27. So that is how we solve questions related to logarithms and its properties. So now this brings us to the last concept that we are going to discuss in the topic basic mathematics, and this concept is related to sets. So basically in this section what we are going to understand is what is a set, how do we represent a set, what are some of the operations, and some important laws. So first, the definition. A set is defined as a well-defined collection of objects. So this is the definition of a set. It is a well-defined collection of objects. Next thing is, how do we represent? There are two ways of writing a set. The first method is known as the roster form, and the second form is known as set builder form. These are basically two forms of representation of sets. So what do we basically mean by roster form? Now in the roster form we basically list down the elements separated by a comma. So this is what do we mean by roster form. And here in the set builder notation, the characteristic property of the set of the element is described. So let us understand what does this mean and how do we write a set in a roster form or a set builder form. Now let us say we have a collection of objects, or here let us take the collection of numbers, and let us say we have 1, 3, 5, 7 and 9. So basically here we have 5 numbers which clearly are odd and they are less than 10. So in the roster form what we do is, let us say the set is denoted by a capital letter A, and we have in this case clearly written down each of the element separated by a comma, and then we write all these elements in a curly bracket. So when we list down each of the element explicitly separated by a comma, this is known as the roster form. So here this example is the example of a roster form of representation of set. So let us try to represent the set in a set builder notation. So here we write the letter A, capital letter A, to denote the set, and the set is written in the following manner. Here X is said to be the element of the set, we put a colon which is read as such that. So A is a set containing x such that x is equal to 2n minus 1, where n belongs to natural numbers and n is less than equal to 5. So this is how we have defined a set. Let us try to understand this representation. So here x is the element which is 2n minus 1. Now what is n? About n we have written that n belongs to natural numbers. So n will take values from 1, 2, 3, 4, 5 and so on. And it is also said that natural numbers n should be less than equal to 5. So if we put n equal to 1, which satisfies these two conditions, 1 is a natural number and it is less than equal to 5, we have 2n minus 1 makes it 2 minus 1, that is 1. So here we get our first element. If we put n equal to 2, we get 3 and so on, we get 5, 7 and 9. So we have all the elements which were written in first roster form by the same from this method as well. And what difference is that this set is just the rule. Here we have just described the rule for selection of elements. And so this form is also known as rule method of writing a set or representing a set. So this is about sets and how do we represent a set in two different forms. Let us now try to understand different types of sets. So here we are now going to discuss types of sets. The first is empty set. As the name suggests, this set is empty and there is no element inside it. So this is just written as A equal to bracket and there is no element inside it. Or other way of representing an empty set is also by phi. So if you find this symbol anywhere, then you can say this set has no elements. This is basically an empty set. Next is Singleton set. Again, as the name suggests, this is such a set which contains exactly one element. So if we say A is a set and it contains a letter A, then this here is an example of a singleton set as it contains only one set. Number 3 is finite set. Now here again, if there is a set whose elements can be counted and the counting ends at some number, then we say the set is a finite set. For example, we have a set A which is 1, 3, 5, 7, 9 and so on. It goes on, but the last element is given to us as 101. So if we start explicitly counting each of these elements, we will be able to count all the number of elements that is present in the set, and hence this set is an example of finite set. Now, what is the meaning of infinite set? So let us say if we have a set which is again represented by letter A, and here in this case the elements are 1, 3, 5, 7, 9 and so on. We have not written what will be the last element in this case, which means the elements will keep on going and we can write the next element after the previous one that we have written, and hence this set is not going to end anywhere and we cannot count the number of elements in this case. So here this is an example of infinite set. So you can understand the difference between a finite and an infinite set. So let us now understand the fourth set. The fourth set is known as a subset. So what is basically a subset? Now consider a set A having elements 2, 4, 6 and 8. Now, so consider now another set here which is written as B equal to 2 and 6. Now, all the elements of set B are present in the set A. If you look at 2 is present in set A, and if you look at 6, it is also there in the set A. So in this case, we say that B is a subset or a part of the set. Sub is basically a part, that is how the name comes. So it is a part of the set A, and hence we call B as a subset of A, and it is represented as B. This is the sign for a subset, and then we write the bigger set A. So if there is another set given to us, let us say C, in the form of 4, 6 and 8, again all these three elements are present in the set A as well. So we can write C is also a subset of A. Now if there is a set, let us say D, which has elements 2, 4, 6 and 8, then since all the elements are present in A, so in this case we write D in this manner. Now here, since all the elements of D and A are same, this can also be written as D as a subset but with a equal to sign, and then we can also say that D is a subset of A also. But there is another definition which is something like a proper subset. A set is said to be proper if all the elements of the subset is not exactly the same with the set that we have previously. That is to say, in this case that we have taken set B, set C and set D, since D is exactly same as set A, D is not a proper subset of A, but B and C are proper subset of set A, and hence we do not put a equal to sign there. We put a equal to sign only if all the elements of both these sets are exactly same to each other. Now the next definition that we have here is of equal sets. Now the definition in this case is pretty straightforward. If a set A is a subset of B, and if B is a subset of A, then we say the two sets A and B are equal to each other. This is the meaning of equal sets. Moving on, now the next concept that we have is the concept of a power set. Consider a set A having elements 1, 2 and 3. Let us now do an exercise of writing all the subsets for the set A. So clearly phi is going to be a subset of the set A, and then we are having three subsets which contains exactly one element. Then we have another set of subsets which will have two elements each, and then we'll have a subset which will be exactly same as the set that we have. So here we found that there are 9 subsets that we can make out of the set A, and the subset and the set of the collection of all these subsets is represented as P of A, and this is known as power set of the set A. And if you want to find the number of subsets that can be formed from a set of n elements, so basically the number of subsets of a set containing n elements is 2 to the power n. Now here, if you see, we have n equal to 3, so 2 to the power 3 is 8, and that is how, if you count, we have 8 subsets. Sorry, I had said previously that we have 9 subsets, 9 elements in the power set of A, but it is actually 8, and it follows the condition or the formula 2 raised to n. So this is about some of the different types of sets. Now there is one more type of set that we must discuss, and that is the universal set. So what is basically a universal set? A universal set is such a set which is supposed to contain all the elements in a particular situation or a scenario. Let us say we are dealing with even numbers up till 100, and there are some sets, let us say A, which has elements like 2, 4, 6 and 8. Then there are other sets B, which contains elements like 12, 14 and 18, and some other set, let us say set C, which is 66, 72 and 78, let us say. So here we are dealing about a case when the elements are all the even numbers less than 100. So U is the way we represent a universal set, and this will contain all the even numbers starting from 2 and ending at 98. So this is the universal set in this case. So universal set is basically a collection of all the sets, or a collection of all the elements in that particular scenario. So this is about the types of sets. Now let me discuss with you some of the operations, but before discussing the operations, let me give you an idea about Venn diagrams. So Venn diagrams is a pictorial representation of sets and the different operations that we have related to sets. So in Venn diagrams, we generally represent the universal set by a rectangle, and we write it as U in the top right corner, or sometimes we also write on the top left corner. So this is how we represent a universal set. This contains all the possible elements. And any other set, let us say if there is any set A which has elements like 2, 4, 6 and 8, let us consider this scenario. So we can represent a set A by a circle, and we write the letter A, that is the name of the set, near to the circle. And if we want to represent other set, it can be done in the following manner. So in this case, we have represented two sets A and B in the form of circle, which is drawn inside universal set. Reason being, universal set is such a set which will have all the elements. So no matter what elements are there in A or B, they are always to be contained in the universal set. So let us now try to discuss some of the operations between sets, and let us also try to understand this with the help of Venn diagrams. Next is some of the operations related to sets. The first of them is the union. So what is basically union of two sets? Suppose we have two sets A and B, then union of A and B is represented as follows, and it is defined as X such that X belongs to A or X belongs to B. That is to say, any element which lies either in A or in B or in both lies in the union. If we want to represent this using Venn diagram, it can be done in the following manner. So here is a universal set U, we have a set A, and we have a set B. All the elements either lying in set A or B or both belongs to A union B. So here the shaded portion represents A union B. This is the first operation that we need to understand in case of sets. Next is intersection. If again we have two sets A and B, then intersection of these two sets are represented as follows. A, and there is an inverted U, and it is defined as X such that X belongs to A and X belongs to B. And if you want to represent it using Venn diagram, we can do it as follows. Here is the universal set. This is our set A, this is our set B. And intersection means the element that we have belongs to both the sets. That is, now if you look at this diagram, this is the area common in both, and this is an example of A intersection B. So this shaded portion represents the set A intersection B. Next is difference. Now, difference of two sets, again, let us take A and B. So if we have set A minus B, so the same sign minus is used for the difference of two sets, and A minus B is defined as X such that X belongs to A, but X does not belong to B. So if we want to represent this with the help of a Venn diagram, this is our universal set. Here is a set A and here is the set B. Now it is such a set which has elements from A, but those elements should not belong to B. So this is the portion which belongs to both, and hence A minus B can be represented by this portion of the diagram. So this is A minus B. Now you might also ask that is B minus A same as A minus B? So let us check if they are same. Some of you might have also figured out by now. So B minus A is written as follows. Here X is such that X belongs to B, but X does not belong to A. Now if we want to represent it using Venn diagram, here we have the universal set and there are two other sets A and B. Now in this case, the element should belong to B, but it should not belong to A. Now this is the portion which is lying in both the sets. So B minus A is this region. And now we have a clear understanding of A minus B and B minus A. And we also now understand that B minus A is not the same as A minus B. Moving on to the last operation in the set of sets is the complement. So if we have a set A, the complement of set A is either represented as A prime or it is also represented as A, and we write a small c as a superscript on the letter A, on that particular set A. And if we want to represent the complement, so basically it is defined as X such that X belongs to universal set, but X does not belong to A. So you can also write in place of but and, as both the conditions have to be satisfied. So in this case, if you want to do the same thing using Venn diagram, you want to represent A complement. Let us try and see what does it look like. So here we have a set U, which is the universal set, and here, now that we need only one set A, let us represent A only, and there is no other set. So now this is a set containing elements belonging to universal set, but those elements should not lie in the set A. So A complement or A prime is represented in the diagram as follows. So this is how we represent A complement. So this is all the operations related to sets. Now there is one other term which is generally used, and that is known as symmetric difference. Symmetric difference is basically the set A minus B union B minus A. So we have A minus B here and we have B minus A here. So if we also shade this particular portion, that is, if we remove the intersection part from A union B, what we have is the symmetric difference of two sets A and B. If you want to represent it using Venn diagram, it can be done as follows. Here is the set A, here is the set B, this is our universal set, and the symmetric difference of two sets can be represented in the following manner. So now that we have understood about the operations, it is now time that we discuss some important laws related to sets. So the first law is the idempotent law. According to this law, A union A is equal to A, and A intersection A is also equal to A. The second law is the identity law. According to this, A union phi, which is the null set, is equal to A, and A intersection universal set is equal to A. The next law is commutative law. According to this law, A union B is same as B union A. Now you can verify all these laws using Venn diagram. Try and make a diagram for A union B, try and make a diagram for B union A, and you will find that both of them are referring to the same part of the diagram. And we also have A intersection B is same as B intersection A. So this is about the commutative law. The fourth law is the distributive law. Now in this case, if we have three sets as A union B intersection C, then it can be written as A union B intersection A union C. Now again, using Venn diagram, you can verify this distributive law. So this is one of the distributive laws. Second could be written as A intersection B union C is equal to A intersection B union A intersection C. So this is about the distributive law. Next is De Morgan's law. According to this, A union B whole complement. So first you have to find the set A union B, and then you have to find the complement, is same as A complement intersection B complement. So this is the meaning of A union B complement, and the De Morgan's law says that A union B complement is equal to A complement intersection B complement. And the second law in the De Morgan's law is A intersection B whole complement is equal to A complement union B complement. Now again, I would ask you to go back and try proving these laws by yourself using Venn diagrams. And so we have basically discussed all the 5 laws that were important in the chapter sets. And now there is some important formula that I want to discuss here before we end up this section. So here I want to discuss the meaning of n of A. So what we have done is we have written n in small, and inside the bracket we have written a capital letter A, and here capital letter A is basically the set A. So if we write n of A, this is basically equal to the number of elements in set A. And one important result here related to this is number of elements of set A union B is equal to number of elements in set A plus number of elements in set B minus number of elements in set A intersection B. So this is the formula for the number of elements in set A union B. And if we have 3 sets, then we can have the formula of n of A union B union C equal to n of A plus n of B plus n of C minus n of A intersection B minus n of B intersection C minus n of A intersection C, and then plus n of A intersection B intersection C. So these are 2 important results related to number of elements in union of 2 and 3 sets. Now if you also need to discuss, or if you are also thinking about the Venn diagram in case of 3 sets, it can be done as follows. I'm sure you might have done it before, but before we end this topic, let me just discuss it briefly. If we have a universal set here and we want to represent 3 sets, then it is done in the following manner. Here is the first set, here is the second set, and here is the third set. Let me give them names A, B, and C. So this is how we represent A, B, and C. And if you are talking about, or if you want to figure out how A union A intersection B intersection C would look like, then if you notice carefully, this is the portion which is common in all the 3 sets, and that represents A intersection B intersection C. So this set theory is very useful in many chapters, and particularly we need to understand when we begin with the topic of relations and functions. So this is all related to set theory, and let us now begin with the next main set of chapters that is there in your standard 11th and 12th portion.